let me try to step back a little bit and first describe what exactly we've been doing in the last couple of lectures. So remember we're studying the problem of statistical learning, where we're assuming that the data that we observe come from some distribution in a IID manner, and we're going to be tested with respect to some loss function on the same distribution, right? And with respect to a random draw from the same distribution. So let's say f hat is the algorithm that we proposed that looks at the data and outputs a function, right? So that's a function that we learned with data. And what we do is we look at the expected loss, where the capital L already has the expectation over a new data point, right? The expectation over the unseen data or drawn from the population. And then we take expectation with respect to the hat, with respect to the data, right? And then what we would like to do, of course, is to try to guarantee that this is small, where f star is the best possible function. Of course, that's our dream. And we would like to show that this goes down with n, right? That as you get more and more data, that you get closer and closer in terms of prediction, closer to the best possible expected loss. Okay, so in the first lecture, we saw that this goal, in general, is not possible because of the so-called no-free-lunch theorem. So there exist bad distributions, and you cannot do anything about it. No matter how well you try, there exist distributions on which you cannot really say anything about that going down with n, right, with a number of data points. So let's say this is the space of all distributions on the data, and you cannot say that your algorithm, such as a deep neural network, will work for any distribution here. Okay. On the other hand, as soon as we start making restrictions to the space of probabilities, then you start getting more and more interesting results. However, unlike the classical statistics or Bayesian approach, where you would try to model the distribution of the data, here we're modeling something about the solutions typically, such as a margin, for instance. Okay? That's an assumption about a distribution from which the data are drawn. Now, if you take a kind of a very small set of distributions, the easy problems, so these are the easy problems. So let's say this is all distributions, these are somehow easy. And I'm going to put it in quotes because I'm never going to define it, because I don't know how to define it. Okay? If you're in an easy case, if you make an assumption about a set of distributions, and that's an easy assumption, right? And by the way, this is not like a single fixed set. I'm just saying, like, you make an assumption that's restrictive enough that will make it possible for you to prove something, right? Then you could get this going down with n in that case. Okay? And we saw an example of that with a hyperplane, with a perceptron under the margin assumption. We've got a nice, easy consequence of just the perceptron bound. As a consequence, this was lecture number 2 in my part. We've got a 1 over n rate times 1 over gamma squared under the assumption that data in the population are linearly separable by margin gamma, right? And this was a strong assumption. So somehow that restricted the set of probability distributions to be a nice, easy set. Okay? Again, I'm being hand-wavy here. Now, if you make an assumption about your population that's not as easy, that doesn't make the problem so easy, then you get into this bias-variance trade-off. In other words, if this is your set of distributions, then you can't attack this directly. So what I mean by that is, somehow if you try to attack this directly, then you're working with a set of functions which are the effective solutions under these probability distributions, right? These are all the possible, let's say, F stars. It's just too large. So you cannot control the fluctuations or the size of that expected maximum over that class. So, in fact, a good way to think about the bias-variance trade-off is it is needed when you don't have such stringent assumptions, and the assumption is weak enough that you really cannot attack the problem all at once. Does that make sense? Does that roughly make sense? So you have to split it into two parts. And one way to split it is expected L of f hat n minus L of f sub f plus L of f sub f minus L of f star. Okay, and this is a kind of a bias variance decomposition, but the only stochastic part is this part. Right? Well, it's this one, but let's put it over the difference. Right? This is the only stochastic part. So the bias variance is decomposition is needed if the class where f star lives is somehow too difficult, too large. Okay? Does that make sense? So if the problem is easy, you don't actually need the bias variance decomposition. You just do, let's say, perceptron. Right? That was an easy problem. There is no bias variance trade-off in that problem. If you do least squares in a finite dimensional case, so d dimension of the problem is less than n, the number of data points, then unless you're trying to get a very precise result about some other properties, if you're just looking at the d over n type of result for the sample complexity of least squares, then it's an easy problem, so you don't need the bias variance decomposition. So again, the bias variance decomposition comes about because you cannot control the stochastics. Okay? It's really because you need to control the stochastics that you need the bias variance. That's why we split it. We split it in such a way that hopefully you can control this part, and somehow, this is called approximation error, somehow understand this part. And of course, ideally you want to balance these two. Does that make sense? Okay. So what we've been doing in the last 4 lectures is analyzing this term only. Now what happens to this term? Well, you can say, let's just hope it's small, right? If you don't want to dig into approximation theory, how one class of functions approximates another class of functions, then you don't, right? You just leave it, and then you say, I'm just going to deal with this term, okay? Then the result you get is only as good as that class, right? So you do as well as the best you could have done with that class of functions f. And now we looked at the particular method for constructing f hat n, and that's just take the minimum loss over the class capital F. Right? That's called ERM. So if it's ERM, then we have an upper bound of expected L of f hat n minus expected empirical of f hat n. Right? This was our 3-term decomposition, if you remember, and 2 of the 3 terms vanished or were negative or non-positive, so we dropped them. So we got to this one. Right? At this point, we said, it's biased. We know that this is a biased estimator of that, and so we don't really know what to do. And now the analysis diverges. You could consider the worst case over f. So just say, so the first one is uniform deviations. we're going to replace this with a further upper bound of expected max over f and f of L of f minus L hat of f. That's one approach. Second approach is going to be based on stability and compression. So perhaps we're gonna do compression today. Compression approach, compression set, stability, and differential privacy. So these are all the different ways you could try to attack this term to limit the bias of this estimator of the expected loss. Okay, does that make sense? So again, I would like to stress the fact that if capital F becomes larger, we have less and less ability to control these uniform deviations. And so at some point we cannot do it anymore, right? So in some sense you have to choose the bias and variance carefully so that you can control that expected maximum in this approach, in the uniform deviations approach. And to understand the uniform deviations, what we did is we just got a very simple upper bound. Again, twice the expectation. So this is expectation over the data. This is twice expectation over data. Of now expectation over epsilons, max over f in f of 1 over n sum of epsilon I, and then maybe a loss function of f of x I, y I. And these are called Rademacher averages. And the nice thing here is that you can indeed calculate this quantity for many interesting classes, and therefore you get an understanding of uniform deviations. Okay? I'm just catching up everyone. Everyone is on the same page. Okay. Any questions about this general layout, what we've been doing?
What about other approaches like ERM?
So other than ERM. Yeah, so you can study stability. Well, for stability you still need to. A close relative of ERM is a penalized ERM, which is like regularized least squares. It effectively restricts this f, but it doesn't do so explicitly. Right? So it allows this lambda parameter, which really controls the size of f. But that's done implicitly, and I don't know if we're gonna go into the details. But again, when you analyze regularized least squares, you decompose into bias-variance in a slightly different way, not like that. And again, one is a stochastic term, very much like what we're trying to understand here. The other one is our approximation. But if you take nearest neighbors, for instance, that's a very different approach. It doesn't go through uniform deviations. The analysis goes through a local type of analysis, and we're gonna do one lecture on local rules such as k nearest neighbors, local fitting, Parsons windows, local polynomial approximation. Other questions? Okay. Yeah, I think one key kind of message that I really want you to take with you is when you analyze a learning problem, you end up with a stochastic term just because you have empirical data, but what you want is something on the population. You want a prediction out of sample, right? And in relating these two, you end up with a term that you may or may not be able to bound. And kind of the larger is the class over which you have to look at empirical minus expected quantities. the kind of the more difficult it becomes. And at some point you cannot control it, right? Because there are too many possible explanations of your data, right? There are too many explanations, and so you don't know which one to choose. It's an inherent kind of difficulty. It's not something that we just we don't know how to resolve. It's really inherent. Okay. So in understanding this kind of easy versus maybe non-easy problems, one can try to summarize the difficulty of this class F by some notions such as a VC dimension. And you've heard probably that there is this big conundrum that VC dimension of neural networks is the number of it's related to the number of units, number of neurons, but typically you take a neural network that is over-parameterized. It has many more neurons than data, right? And so if you look at the VC type of approach, you say, well, it can't work because that complexity of the class F is too large. So you shouldn't be able to control these the maximum, expected maximum, right? But then there is often another aspect of the problem, such as the margin, that mitigates this huge dependency on the number of neurons. So what I'm going to do now, today, is a relatively classical large margin analysis that is applicable to neural networks as well. And as you will see, the number of neurons or the dimension will not explicitly appear in those derivations. Okay? Any questions? Okay, so today, large margin analysis for classification. One result which I maybe mentioned in passing, but I didn't spend too much time on it. But if you look at a class G, so who does not know what a VC dimension is? 1, 2, 3, 4. Okay. Okay. It's some measure of complexity. Let me not define it. Let's just say if you've got a class of functions that map Z to let's say f of Z in plus minus 1, then either VC dimension of F is finite or VC dimension of F is infinite. Okay? So that's like a litmus test, whether the class is simple enough or it's not simple enough. Okay? Perhaps I can, let me call this G. G. Doesn't matter. We don't have to erase. So then when you look at Rademacher averages of G projected onto Z1 through Zn, then now this is a subset of patterns of plus and minuses that you can realize on these data. Okay? So remember the picture. This is the class of functions. Now, of course, they're binary now, so they're only plus minus 1. But if you put all the possible on Z1, this function is plus 1, minus, 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 plus. That's one pattern of plus minus 1s. And then as you put all these patterns together, then for a VC class, this would be upper bounded by something like square root of VC of f divided by n. And for a non-VC class, so this is for a finite VC, and for a non-finite there exists Z1 through Zn such that this complexity is 1. So you cannot, it doesn't go to 0, right? So somehow VC dimension is first of all, it's a loose notion, right? Why is it a loose notion? If it's small, if it's finite, then it does control Rademacher averages. But if it's not small, there exists some data points on which you cannot control the Rademacher averages. But who cares? Who cares about the existence of these points? Maybe they're rare. Maybe you'll never see them, right? That doesn't necessarily preclude you from. It's not a lower bound, right? It's not a lower bound. Okay, so this is a 3-minute introduction to Vapnik-Chervenkis theory. I'm not going to say anything more except this. So what I would like to do is I would like to I remember Tommy wanted to at some point to get rid of VC theory altogether. So I snuck in a 3-minute introduction. Vapnik-Chervenkis theory. But typically, when you're implementing a classifier, you don't just work with some abstract class of functions which give you binary valued outcomes. It's kind of unwieldy to have a classifier that just directly gives you plus minus ones. What you typically do is you have some class of functions which are real valued. X maps to f of x in real, and then you get this induces a class of classifiers given by the sign, right? So let's call I of f is the induced class of x maps to sine of f of x as f ranges, right? And this arguably this is the typical situation. So typically you're working with some real valued class, and then you just take a sign. So for instance, with hyperplanes, we took a real value that's the product of w and x, and then you just look at the sign. Is it positive? Is it on this side, or is it on the other side, right? And the whole point now of today's lecture is to say, if you do this for this class of functions, then you're being perhaps overly pessimistic. You can do better. And you can do better because of this margin analysis. Okay? So what is a margin? Well, you can have a hard margin, which is there exists an f in your class of functions such that for any index I, yi times f of xi is at least gamma. Right? And so the picture for that is that you have f defines a classifier, a separating boundary, and there are pluses here, and there are minuses here, and there's a no man's land somehow, right? Does that make sense? So you don't have any adversarial examples in the more recent language of this problem. Question?
We are considering the set F for all classifiers. Are you considering all possible classifiers in the world of the classifiers that you consider in your specific algorithm?
It's going to be a fixed set of functions, and we're going to be choosing from this set of functions, right?
It's an algorithm.
So our algorithm will minimize something over this class of functions. It may be empirical risk minimization, so just minimize some loss. Ideally, in what I'm going to say, you would like to minimize the loss and maximize the margin. Okay. Now, this picture is a little bit misleading because, so if this is a boundary, the way that I drew it suggests a geometric margin. The distance to the decision boundary is at least gamma. But the way that I wrote it is just in terms of the values. It's at least gamma, which really now depends on the Lipschitz properties of f. If f is very steep, then you can move a little bit in the x space and already satisfy the margin, right? So translating this to a notion of a geometric margin, distance to the boundary, requires understanding the Lipschitz properties of the function, okay? Just a side note. Okay, so that's a hard margin. What is a soft margin? There exists an f in F such that the proportion, so 1 over n times the cardinality of the set I such that yi f of x I is less than gamma is small. Okay. Now this is something you can try to check in practice. You've trained your neural network. You look at how many data points. Maybe they were correctly classified, but not quite correctly enough. Good.
How do you define the cardinality of this?
Cardinality is just counting.
Oh,
Just go through all the points and check if it's less than gamma.
do you have a specific formula for small with that small?
No, I don't. So this is a yeah. So let me put it in quotes. Okay? Yes, question? This is in the sample. Yes.
Is there some action for considering the case risk again?
Break tie, it doesn't matter. Any other questions? So what we're hoping is that our problem somehow is simple enough that one of members of our class of functions, let's say a neural network, not only separates the data, but it separates the data with a margin, right? That's our hope, right? That's what we're gonna call easy, right? Of course, it's not easy, but that's our notion of okay, maybe it's not easy like the small easy that I drew, but okay, it's gonna be manageable. And what we're going to do today is to show that if you're willing to believe that, let's say, a neural network can separate your data and not have too many gamma mistakes, we're going to call it gamma margin mistakes, then this VC analysis is irrelevant in some sense, right? Then I can just tell you a generalization bound or why the method should work out of sample just based on the Rademacher averages of the class F. And that has nothing to do with the VC dimension. And therefore, the number of neurons in the neural network has, is irrelevant. So the whole overparameterization story is irrelevant. Okay? Good. And the proof is, I distilled it to essentially 3 lines. So if you can bear with me for 3 lines, we're going to be done. I'm going to do it in expectation, just because things are simpler in expectation. Typically, I would write things with high probability something holds, right? It's nicer, but I'm just going to do it in expectation. You can, at home, convert it into a high probability result. So I'm going to look at the indicator loss as a function of y times f of x. So when y times f of x is negative, you make a mistake of 1. That's the indicator loss. So the black is indicator that y times f of x is less than 0. I'm going to propose 2 more losses, 2 more loss functions. One is going to be, let me put gamma here. One is going to go like this. It should be in the same level 1, but I'm just drawing it for visualization. And then it's going to slope down. And then it's going to stay at 0. Okay, so this one I'm going to call it phi of y f of x, and that is 0 if y f of x is larger than gamma. It's going to be 1 if y f of x less than 0. And it's going to be 1 minus s over gamma when y f of x is between 0 and gamma. This is the s, right? Okay? Is that okay? I just put down the formula for this transition. So let me call it a ramp loss. So it kind of looks like a ramp. And then I'm gonna have yet another, the third one. I'm gonna put it like that, and it's gonna continue until gamma, and then drop. And then continue at 0. Right? And that I'm going to call a psi of y of x to be the indicator that y f of x is less than gamma. Okay? We okay? Okay, so I can define L phi of f to be, well, as before, it's expected phi of y f of x when x and y are drawn from the distribution P, right? I'm going to use black from now on. And same thing with the psi. And the empirical, right? Let me do it here. The empirical, let's say psi. I don't know if you can distinguish my phi from psi, but roughly is going to be 1 over n sum of, and actually let me write it out. I'm going to write it out as an indicator that yi f of xi is less than gamma. So what's the meaning, this is of f. So what's the meaning of empirical with respect to psi of f? In words? For function f, it's the proportion of when the margin is less than gamma, right? It's exactly what I wrote here. This is exactly it, right? So I'm hoping that in my class f, there is one function or more such that the L hat f psi is small, right? So I've captured somehow my prior knowledge that the decision boundary should look like that, and there are only a few proportion is small of the margin mistakes, right? Again, a margin mistake is when this, if this is, let's say, gamma, if this red moves into this region, that's an indicator of a gamma mistake, right? It's a gamma mistake even before it crosses the decision boundary. Of course, if it's on the wrong side of the decision boundary, it's for sure a mistake. But this will count even if you're not confident enough. It will count against you, right? If you produced a prediction and you said, 0.1. Yes, you're correct, but not confident enough, sorry. Okay, so you make a mistake. Does that make sense? So the nice thing about these three functions is that they dominate each other in an obvious way. So they dominate each other in the sense that the indicator is less than phi is less than psi, right? Point-wise, and you can see it from the picture. But it also means that for any f, things like this happen. So the 0,1 loss of f is upper bounded by phi of f is upper bounded by psi of f, and the same thing for the empirical. And this is the indicator, right? The 0,1 indicator loss. So empirical of f less than phi of f less than psi. Okay? Any questions about this? Obvious? They're positive, so it's all clear. Actually, positivity is not even important here. Okay. Now, if I look at the expected maximum over f in f of L phi of f minus L hat phi of f, right? I'm looking at how empirical quantities relate to expected quantities, but I'm looking specifically at the phi loss function, right? At the ramp loss function, the green one. Now, because this guy is lower bounded by 0, 1, and this guy is upper bounded by the psi, I can lower bound this by expected max of 0, 1 of f minus L psi of f with a hat, right? I'm not putting parentheses, but it's a max over, of course, over the difference, right? This step is clear to everyone? How about, now, we need to understand this quantity. And my claim is that this is upper bounded by, well, the first step, what do? How do we upper bound uniform deviations? We do the symmetrization lemma, and we get twice the Rademacher averages of class. Twice expected R hat of phi of f, right? Where phi of f is just the loss function composed with every function in f. But phi is Lipschitz. It's 1 over gamma Lipschitz, right? The slope of that transition, the slope of the ramp is 1 over gamma. So we can get rid of the phi by one of the properties that you saw before. And therefore, this is upper bounded by 2 over gamma expected R hat of f. By the way, I'm not writing projected onto the data, but it's to be understood, right? That these are evaluated, these are Rademacher averages evaluated at the data. Now these are evaluated at both x and y, but now that we get rid of the phi, there is only x. Y washes away. Y goes away. Actually, for the same reason that you're going to do in the homework if you haven't done it. Now, this holds for maximum of a function in the class. So it holds for all the functions in the class. So no matter what algorithm you're going to use, if the algorithm chooses from f, let's say you work with linear functions. If the algorithm chooses from f, this will apply to your algorithm. That's the beauty about taking the max, because it will apply to any data-dependent algorithm that learns from the data, right? It works for all functions at the same time chosen from f. And so let's say you have f hat n chooses or learns but takes values in f, then what we can conclude is the margin bound, and we're done. So what is the margin bound? The bound says for that f hat that takes values in f, the expected out of sample 0, 1 loss of f hat n minus the empirical, okay, the expected empirical psi loss of f hat n is bounded by 2 over gamma. Did I say RA of expected r hat of f. Okay? Or I can put an, I can bring this term to the other side. Maybe this is a bit more pleasant to look at this. Right? Now, what's the meaning of this? If the Rademacher averages of the class are nicely behaving, so you can control the capacity of your model, which is, I mean, you have to have that. And gamma is not too small, you don't choose 0 for your gamma. And the number of margin mistakes is not too bad. Then you have a guarantee that the expected performance on the new sample is good. Right? That's it. It's a one-line, really one-line proof. That's the highlight of large margin theory that was explaining the good performance of support vector machines. Or it's one way to explain the good performance of support vector machines. This was the method that was used before deep nets. You can compute the same things for deep nets. And there are papers showing what is the expected number of margin mistakes with a gamma margin, and what is the complexity of the class of models. So, 20 years ago, when people looked at support vector machines that map your problem into RKHS, the reproducing kernel Hilbert space, and then they do classification in that space, right? The decision boundary is kind of crazy, and it's an infinite dimensional space. So people first said, well, VC theory cannot explain this because there are too many parameters. The model is over-parameterized. You can't have a meaningful generalization bound, right? Hopefully this reminds you of something. It's exactly the same thing that people now say about neural nets. So one of the answers is, well, the VC dimension does not even enter here. It's irrelevant. For the margin analysis, you can be in the infinite dimensional VC class. The margin bound is still valid. Right? And it gave a justification to methods that try to maximize the margin in the data. This is a justification to try to minimize this, right? I mean, once you see this bound, you say, okay, I'm gonna go after this, right? I don't want to do just empirical risk minimization with a 0-1 loss. I want to minimize the margin. Maximize the margin as well. I want to have a decision boundary that not only correctly separates the data, but also goes through kind of like a middle, right? Yes? Lower bound on the complexity of the model, but I don't really know I don't really know. Then I would have to quantify this somehow. I don't know how to do that necessarily. So there are a couple of things that I swept under the carpet. One thing that I swept under the carpet is you can get this result in high probability, just as you do in the homework. In high probability, everything works. So in high probability over the draw of the data, right? So why is that nice? Because then the statement is like this. So a high probability statement with probability at least 1 minus delta L of f hat n, let's see that, is upper bounded by L hat psi of f hat n plus 2 over gamma r hat of f plus, and there are some terms that go as log 1 over delta divided by n. Okay, so I'm going to skip those terms so I don't confuse it. Right? So then it really is about the interpretation. We're discussing this the other day. So what's the interpretation of these results? It says, of course, you've got a data set in front of you, right? You don't really draw the data set. But you have to be in this mindset that my data set came from the population as an independent draw from this population of, let's say, images. And I know that with probability 1 minus delta, the statement is correct. And therefore, I'm confident that my data set is one of the 1 minus delta 1, right? One of the, so I'm confident that this statement is correct. Does that make sense? If I'm confident, then okay, then I have a guarantee that the out-of-sample performance of my method is controlled by margin mistakes plus some complexity. It's a rubber stamp that this method will work out of sample if you observe in the data that you've got small number of margin mistakes and you're working with a manageable class of functions. Okay? Yes?
Did you say in the expectation statement, you said you try to find a method that minimizes the margin? The gamma...
Maximize the margin.
But the margin, the gamma would also kind of explode on the other side.
Oh, right. Okay. So another thing that I swept under the carpet is that this method, if I were to minimize gamma margin mistakes, my method better know what gamma is, right? But in fact, I can, once I have the high probability statement, I can take a union bound over all gammas. So in fact, I can make a statement for all gammas. No matter what the margin is, I can optimize, after having the data, I can optimize the margin that will balance those two terms. And in fact, people have done this optimization. So if you look at the paper of Bartlett, Foster, and Tilgarsky, for instance, just last year about the complexity of neural networks and the margin analysis applied to neural networks, then they optimize over this gamma. Because the statement will work for any gamma. Other questions?
How do you control complexity, Rademacher numbers in neural networks?
So that's going to be a separate class, right?
Okay.
We'll have a separate class on that. So I'm not telling you how to control this. Right? Actually, let's do it for. This is a good point. I want to. Can I erase this? By the way, for a large margin theory of classification, it took a lot of years, and I gave you one line, right? One line proof. I tried to distill it really to like a one line argument. Right? But there's a lot written on it, so you can read more on your own. Okay, so this is a side. So we talked about things like Rademacher averages of a ball in n dimensions with respect to, let's say, L2, right? So it's just a sphere, right, or a ball in n dimensions, right? This was the object. If you remember, we saw that it's just a 1 over square root of n, right? So this is equal to 1 over square root of n. But what I'm telling you here is that I need to take a class f, and let's say f is a class of functions x maps to wx, where w is now constrained in L2 norm. Okay? And let's say for simplicity, all the xi's are bounded by 1 as well. All the data lives inside a ball. Now I need to talk about Rademacher averages of f projected onto x1 through xn. Now this is a ball, but these objects live in d-dimensional space. So, So W and X live in RD. Now, what is the meaning of this? This is just a, I take one W and then I evaluate on x1, xn. And then I take another W, W prime, and I evaluate it W prime xn. And then I keep going over the different W's, and these are all the different vectors that I get. Do I get a ball? There is no rotational symmetry, so it can't be a ball. It has to be something else. So what kind of object? As I enumerate all these vectors over all the different W's, what is this? Actually, I don't know what this object is, so I'll leave it to you. I don't know what this is, right? As you try to enumerate over all the W's in the ball. But I do want to stress this difference. One is I know what my values are constrained like, and the other one is I know what my parameters are constrained like. Okay? And I want you to understand this difference. What I'm looking for, this is the important object, not that one. This was just an exercise. This is the important object, and it's actually not too clear what the shape of this is, because you have to go again through all the W's and look at the vectors obtained by evaluating every W on the sequence x1, for example. Is the problem clear? When you have these points on the sphere, right? And now you take one W, and then you project everything onto this direction, right? That's the meaning of the inner products, right? And now you got some values, and that's the vector now. And now you rotate the vector, and then you get a different projection. And so as you rotate, what kind of projections onto this vector can you realize? Yeah, it's not clear. It's ugly at best. Okay. So, the thing is that you don't have to actually explicitly describe this projection, right? All you have to do is to look at the, so what is the r hat of this f, this particular f? Well, let's just write it out. It's a expected epsilon 1 through epsilon n. Let me just say epsilon instead of writing it epsilon. Max over W of norm 1 of sum of epsilon I W xi. That is the definition. I just wrote down the definition. Right? Except instead of first writing out what the definition of f is and then putting it in, that's the same thing, right? Is everyone clear? That is the same thing, right? Because as I go over the different W's, I'm looking at correlation of the random signs and the values of the function on my data, right? That's my richness of this class. But let's write it out. This is linear, right? So I can take W out. Yes? Can I, if I have an inner product, I can take the W out. So that's expected epsilon max W bounded by 1 W times sum of epsilon I. By the way, I didn't normalize, so this is n times xi. Yes? Anytime you have a maximum over W times something, you're itching to do what?
Kernels?
Not necessarily kernels, but just to write it as a dual norm, right? Because that's the definition of the dual norm. Right? It's much simpler than what you were thinking. What's the dual to L2? L2. And now I can do the thing that I did last time, which is put a square on it. Everyone sees this step, right? I put a square and take square root, nothing changed. And then by Jensen, I take the square root out. This is a very useful trick, right? Now, what happens to the cross terms when I open up the square? The cross terms are 0 in expectation, right? Because they have epsilon I, epsilon j, xi times xj. These are the cross terms. So what remains is just the epsilon I squared, which is 1, times xi norm squared, right? Which is at most 1. So the sum from 1 to n of ones is just n, and there is square root outside, so that's equal to it's upper bounded because of this condition. It's upper bounded by square root of n. And if I were to normalize by 1 over n, then Rademacher averages would be 1 over square root of n. Right? So in this case, this is bounded by 1 over square root of n. Okay? I just divided by both sides by n. It deceptively looks the same as this one, but for wrong reasons. It's just a coincidence. In particular, if I had a L1 ball here, remember what this number was for L1? It was 1 over n, right? If I define my class of functions where W, the parameters are bounded by L1 in L1 norm, then it makes sense to bound these by L infinity, because then the product of them by Cauchy-Schwarz is bounded by 1, and so the function values are normalized to be between -1 and 1. In that case, this is L1 norm, and the dual to L1 is L infinity. So I'm looking at L infinity of a random vector, or of a sum of random vectors. So it's the largest coordinate after I add up n random vectors. Now the maximum over a coordinate behaves like square root of log number of them, right? Remember? So I'm going to get, so for L1, for a W in L1 bounded by 1, I'm going to get square root of log d over n. Okay. So that's very different from a 1 over n. Right. You can work it out at home, or maybe I put it in the at some point in the slides, but I didn't give you enough details, but you can try to do it yourself. So it's just by accident that we got the same result for L2. Okay. Now, here's the punchline. Let's go back. So forget about the L1 case. Let's go back to this one. Let's go back to this one, right? And let's think of a perceptron. So what is a perceptron? It's a hyperplane whose norm is bounded by 1 in the L2 sense. So that's exactly this class. So perceptron is actually working with exactly with this class. Okay. Now, of course, when you update perceptron, you go away. You don't normalize. But to make a prediction, you anyway would normalize. It doesn't matter how the length of the vector, right? What is important is that the W star, the one that gives you the gamma margin, is norm 1, right? That's where this constraint comes in, right? That's your prior knowledge about the problem. I think that there's going to be a vector W star which will give me a margin of 1 of gamma. So what result are we going to get for perceptron? So let's see. Implication for perceptron. So the class F is this class, and we get expected L01 of F hat, which is really our, let's say, perceptron, but this will work for any, in fact, for any hyperplane, is upper bounded by the number of gamma mistakes plus 2 over gamma times, that is, well, I just erased it, 1 over square root of n. If I have a hyperplane that completely separates the data, by the way, this will hold for any learning method with values in F, which is this class. So for any method that chooses a hyperplane, I can guarantee that future performance of this hyperplane is at most the number of gamma mistakes it makes plus 1 over square root of n and 1 over gamma. Right? So what we've done now is we've extended perceptron beyond the what's called the realizable case, where there is a hard margin, right? Now, this can be a soft margin, there could be a number of mistakes, but if you've got this number relatively small, then you've got a good guarantee for future. Question? Yes?
So when you say for any learning method union for any f hat?
Yeah, for any f hat n, except I didn't want to say that, as you see, because because f hat n depends on the data, and this is the expectation over the data. So, right? Does that make sense? So if I have my right, f hat n is on the one hand it's a function, on the other hand it's something that I learned from the data, and this is the expectation over the data. So I didn't want to say here for any f hat n. That's going to be the case. Yes. Yes. Thank you. Thank you. But this high probability will also be true. Maybe it's better to write the high probability statement. Okay. Do we recover the perceptron result that we got in the first lecture? So there it was separable, and therefore this was 0. Let's erase both expectations. It will be easier. So with probability at least 1 minus delta for any learning method with values in f, this holds, and then there is something which I'm not going to specify, log 1 over delta over n, some constants, and so forth. Okay? So that's the guarantee. So if I observe no mistakes, which was the case when I run perceptron to convergence, right? This was the second consequence in our lecture. This is 0, and so I get out of sample performance for the perceptron is bounded by 1 over gamma times 1 over square root of n. Did we recover the result we had?
No.
What was the result we had for the final hyperplane? Yes. fact, it was 1 over gamma squared, because that's the number of mistakes. If you remember how we got that result, it's 1 over gamma squared and 1 over n. So in some sense, it was twice faster than what we've got here. So this result works without this hard assumption of linear separability. It works under a soft margin, right, which is more natural. Probably you have occasionally you get cats which look like dogs and dogs that look like cats, right? But we get a kind of a larger sample complexity. If you set this to epsilon, you get sample complexity is like 1 over epsilon squared rather than 1 over epsilon. Right? So that was this is the difference. So one could get a result that would recover that perceptron result, but it's much more difficult. So I'm not going to even go there. Right? It's just a simple consequence of what we discussed. Any questions? Questions? So again, the point here is that these hyperplanes could be in a d-dimensional space where d is very high, and in particular d is the number of neurons if you think of hyperplane as a one-layer neural network. It seems like I have to turn everything into neural networks. That's what gets students excited, right? So it's a hyperplane is a one-layer neural network without a hidden unit, and d, the dimension, is just the number of units in that layer, right? So as you see, d never appears here, right? So even the premise that the neural network generalization has to depend on the number of units in the neural network is not true, right? This was a 5-line analysis that shows that you can get a result without the number of units, right? For one layer. Of course, for more layers, it's going to be more complicated. Questions? Right. Does that make sense? Yes?
So I think for the problems, if you scale it up, then gamma might be small.
Yeah, so right. So this is kind of like a posteriori result, right? It says, you train your model, and you look at the margin distribution. Pick the best gamma you can that balances this and that. And that will give you a guarantee on the out-of-sample performance.
Hierarchy analysis that say that high probability is
So in the original 2002 paper by Kolchinsky-Panchenko, there is some analysis that looks at theoretically at the empirical margin distributions. The paper is called empirical margin distributions. It looks at them theoretically and how they relate to the population margin. Any other questions? So the question is, should I start the compression, or should I leave it for next time, or should I describe something else? Next time, okay. Should I describe something else, some other result? I'm kind of in between. Let's see if I can do something else.
Just a general comment in regularization networks. You control the complexity and the Rademacher number by controlling the norm of the weights.
In neural networks.
Well, kernel classifiers.
Right. So what?
In neural networks, as we'll see, you can do that, but you don't need to. That's an interesting puzzle.
So right. Well, okay. So one thing that Tommy is saying, let me repeat this, is we've got this tool, which is this Rademacher averages, and that's a way to understand classes of functions with which you're working. If you're working with neural nets, okay, you might have to compute this. And the way that you compute this is you upper bound it. You see how we got upper bounds on this? You upper bound it by some norm. And we restricted the weights of our one layer neural network without the hidden units. We restricted that norm to be 1. And in the same way, we'll see that you can say that for all neural networks with bounded norms of the weight matrices, we can get a result. But this is not the only way to proceed, right? I'm just showing you one path to getting generalization bounds, to analyzing out-of-sample performance. There are other methods. In particular, I will describe at least stability, compression, differential privacy type of thing for randomized methods. Is there something else? I think that's about it. And you had some other things in mind that you will present.
What I was saying also is, in all this argument is important that the algorithm somehow controls the complexity.
Yes, that's right.
And one way you do this in what is kernel machines is by regularization.
That's right.
Or by minimizing the functional in a ball.
Yes.
In terms of the norm of the weights.
Right.
In neural networks, there is often no explicit control.
Yes. Yes.
That's
Yes. Okay. So right. So okay. Let me elaborate on this point.
Yeah.
That's a good point. So
it's a comment also for future use.
Right.
Future classes.
So actually, this came out from discussion on Friday. Why do we do this actually? What's the point of these bounds, right? This was one of the comments, right? I mean, it's a good comment, right? Like, what is the practical implication beyond the pure joy of understanding that you've proved something on the population that you don't know, right? Like you've proved something, right? This is what I want, right? And I've just proved that it's small, so there's certain pure joy to that, right? But beyond this, like, what are the algorithmic implications of this, right? And so one implication is that whatever we get as a complexity, you can use to regularize the problem, right? And that should be a proper way to regularize your problem, right? You can't just minimize over all functions in the universe, right? You have to have some kind of prior and the right notion of complexity.
The algorithm has to contain something.
The algorithm has to contain some regularization in it, right? Some control of capacity, right? And so by understanding these complexities, you understand what kind of capacity can be used to regularize the problem. So for instance, as you can see, by controlling the norm of the vectors, you got a very nice bound. 1 over square root of n is essentially the best you can hope for Rademacher averaging, right? That's like, if you've got two functions which are different enough, that's already 1 over square root of n. So having a whole ball in L2 and getting the same for the price of, of 2 functions is really miraculous, right? So it tells you that L2 can serve as a certain regularizer. And in fact, you can relate these Rademacher averages to what should be the penalty. Should you do Tikhonov regularization with L2 norm? That's essentially what it is, right? Tikhonov regularization is you are in RKHS with infinite dimension, and then you're putting L2 norm on the coefficients, right? That's exactly what you're doing, right? Some weighted L2 norm. And that comes out of this, right? So that comes out as a proper way to regularize a problem. But now, when you talk about neural networks, now maybe it's a product of norms of the weights of the layers, for instance, right? So that could be now a regularizer that's meaningful, and you can try to implement it in practice. So these go hand in hand. You understand the complexity and how it controls these empirical fluctuations that can mislead you you see something on the data, but you see something else in the out of sample, and the understanding of this complexity tells you how to regularize the problem, right? So there are things like, I know, path SGD is one example where you take that a complexity and you actually penalize your neural network training with that complexity. And you can already see it here. Like if I kept it, let's say I kept it here as a B, right? So the norm of the W is bounded by B, right? This is B. Then it would be just be times B, and this would be B, right? So here I would have here I would have 2 times B. But in fact, by working a little bit harder, you can replace the L2 norm of the W here. Let's put W hat. W hat. You have to work a bit harder, but something like that is possible, right? So this suggests that you should be optimizing, right? We're in business of optimizing upper bound, right? That's pretty much how everything works, right? You get an upper bound and then you optimize it.
So minimize that.
So you minimize margin loss and complexity of the model as an L2 norm, right? So that exactly tells you the algorithmic implications. Yes?
Could this be extended to non-linear kernels?
This extends to kernels, yes. You put k of xi here, and then this becomes square root of sum of k of xi. And so if you have a kernel that has a bounded reach, it's the same value, essentially.
Can you base your choice of kernel on what the complexity is, like you would?
So yes. So each choice will give you a result, and I some of them can be dominated, but some of them are incomparable. So you can't. It's hard. It depends on the problem at hand. Yeah, that's a good question. Yes.
So from your networks, can you say that dropout works as something not executing?
So there is work on that as a regularizer. I'm not. It's not on the top of my head. I can look into it. Other questions? Yes.
So this is only one way to keep the upper bound, and there are many other ways.
Yes.
But like, if all those ways fail, you can't say the generalization error cannot be upper bound.
Yeah. If all the approaches fail, you cannot say that.
Like, if there's something on that flavor, then you can say something. This generalization error is for sure going to aberrate.
If I understood correctly, if none of your approaches work, it doesn't mean that the result is not true, right?
Yeah.
Okay. Happy to answer questions. See you on Wednesday.